Hello friend, welcome to Science for Sleep. Tonight, we are going to spend some quiet time with a food that may seem simple at first. It is soft, sweet, familiar, and easy to overlook. Cake is often just there, waiting on a plate at the end of a meal, or resting under candles at a birthday party, or sitting in a bakery window behind clean glass. Most of the time, people do not stop and think very hard about it. They just smile, cut a slice, and enjoy it. But cake is more interesting than it looks. A cake is never only a cake. It is flour and sugar, heat and air, time and texture. It is a set of small changes happening in the right order. Dry powder becomes batter. Batter rises into something light. The surface turns golden. The kitchen fills with a warm smell that many people know before they can even explain it. That is part of what makes cake such a good subject for sleep science. It is gentle, it is familiar, and at the same time, it is full of tiny hidden events that are easy to miss. As we settle in tonight, if you enjoy calm science like this, you can subscribe to the channel, leave a like, and come back whenever you want something quiet to listen to at the end of the day. And if Science for Sleep has become part of your evening routine, that simple support really helps. Cake is also a good topic because it lives in two worlds at once. In one world, cake is science. It depends on structure, moisture, temperature, and timing. Small changes can matter a lot. A little too much mixing can change the texture. A little too much heat can dry it out. Not enough air can make it heavy. The right balance can make it soft, tender, and light. In the other world, cake is memory. For many people, cake belongs to moments that stand out. Birthdays, weddings, holidays, family dinners, school parties, a visit to a grandparent's house, a slice shared with coffee in the afternoon. Even people who do not eat cake very often usually have some picture in their mind when they hear the word. It may be a chocolate layer cake, a plain yellow cake, a cheesecake, a sponge cake, or a small piece from a grocery store bakery in a clear plastic box. That matters because food is never only about nutrients or recipes. Food also carries emotion. It carries habit. It carries place. Sometimes it carries a whole memory in a single smell. Cake is a very good example of that. It is also one of the clearest examples of how science hides inside ordinary life. People often imagine science as something distant, something found in a lab, or written in large books, or explained with charts and hard words. But science is also in a mixing bowl. It is in the way butter softens at room temperature. It is in the bubbles trapped in batter. It is in the starches that swell, the proteins that set, and the sugars that help the surface brown in the oven. Even the smell of cake tells a scientific story. So does the crumb, the sweetness, the softness, and the way a slice can feel rich and light at the same time. And cake is not just one thing. It can be airy or dense, simple or decorated, homemade or factory-made, plain or filled with layers of cream, fruit, or chocolate. It can be a daily snack in one place and a special event food in another. It can be rustic, elegant, playful, or carefully designed. So tonight, cake gives us a very peaceful path to follow. It lets us look at history, chemistry, heat, texture, and memory, all through something that feels warm and familiar. It gives us a topic that is soft around the edges, but full of detail once we begin to look more closely. And sometimes those are the best subjects of all. Not the loud ones, not the urgent ones, just the quiet things that have been sitting in plain sight the whole time, waiting to be understood a little better. And when we do try to understand it, one of the first things we notice is that cake is harder to define than it seems. Most people feel that they know a cake when they see one. A birthday cake, a loaf cake, a slice of chocolate cake, a sponge cake with cream, a plain cake dusted with sugar. These all belong together in a way that feels obvious. But the closer you look, the more the edges begin to blur. Cake is not quite bread, though the two are related. Both are built from grain, liquid, and heat. Both begin as a mixture and end as something baked and shaped. But bread is usually made to be sturdy, chewy, and useful. It is often thought of as an everyday food, something meant to support a meal or stand in for part of one. Cake moves in a softer direction. It is usually sweeter. It is usually more tender. It often contains more fat, more sugar, and more richness. It is meant to feel light, pleasant, and easy to bite through. Bread asks the mouth to work a little. Cake usually does not. It gives way more quickly. It breaks into crumbs. It almost seems designed to disappear. That softness is part of the point. A cake is usually built to be delicate, even when it is dense. It may be airy and full of tiny holes, or close and rich with a fine crumb. It may be stacked in layers or baked in a simple pan. It may be covered in frosting or left plain. But in most cases, cake aims for comfort rather than strength. That is one way to tell it apart. Another is purpose. Bread is often expected. Cake is often offered. Cake appears at birthdays, weddings, holidays, school events, family dinners, office parties, and quiet afternoons when somebody decides that the day needs a little sweetness. Even a very simple cake carries a feeling that it is slightly extra, slightly beyond the basic needs of hunger. It is food, of course, but it also feels like a gesture. And yet cake is not one single thing. Some cakes are tall and fluffy. Some are low and dense. Some are barely sweet at all. Some are almost closer to custard. Some are made with wheat flour, while others use ground nuts, rice flour, or other starches. Some are baked. Some are steamed. Some are served with fruit. Some are layered with cream. Some are eaten by hand. Some are cut into careful slices. So maybe the best way to think about cake is not as one exact recipe, but as a family of foods. What ties that family together is not one strict rule. It is a pattern. Cake usually begins with a starch of some kind, often flour. It usually includes moisture. It often includes fat. It often includes sweetness. And it usually depends on some method that helps create a texture softer and more fragile than bread. That method may involve whipped eggs, baking powder, baking soda, steam, or simple careful mixing. Different cakes solve the same problem in different ways. How do you take simple ingredients and turn them into something tender? How do you make a food that feels gentle? That question sits quietly underneath almost every cake ever made. And once you start thinking of cake that way, as a soft structure rather than just a dessert, it becomes easier to see why it has changed so much over time. The cakes people eat now are not the same as the cakes people knew hundreds or thousands of years ago. They could not be. The tools were different. The ingredients were different. Even the idea of sweetness was different. So the cake we know today did not appear all at once. It had to grow into itself slowly, over a very long time. To see that slow growth, it helps to go very far back, to a world without electric mixers, without white sugar in paper bags, and without the kind of soft, even flour that now seems normal. In ancient Egypt, bakers were already working with leavened dough by about 2600 BCE, and they used some of the earliest known ovens, tall clay cylinders made from Nile mud, with a fire below and a baking chamber above. That was advanced baking for its time, but it did not yet produce the light birthday cake most people picture today. The sweet baked foods of that world were usually closer to dense breads, flat cakes, or rich grain loaves. In Egypt, sweets could include cakes and pastries mixed with chopped fruit, nuts, or syrup. But the main sweetener was usually honey, because refined sugar had not yet spread into the Mediterranean world. Honey itself was valuable, so people also used dates and carob for sweetness. One ancient Egyptian detail is especially easy to remember. Pastry specialists could be known as workers in dates. Even that title tells you what sweetness looked like before sugar took over. So the earliest ancestors of cake were not fluffy. They were practical, grain-based, and often heavy in the hand. Their flour was rougher because milling was rougher. Their sweetness came from what fields, orchards, and hives could provide. Their texture depended on hand grinding, coarse meal, and uneven heat. A modern sponge cake wants tiny air pockets and a very fine crumb. An ancient honey cake was more likely to feel compact, nourishing, and sturdy enough to travel from hearth to table without much ceremony. And yet, these early cakes already had something deeply familiar about them. They were tied to moments that stood apart from ordinary meals. In the Greek world, from at least the late Minoan period in the 2nd millennium BCE, honey-sweetened cakes and pastries were prepared not only for eating, but for offerings, festivals, and sacred rites. Ancient Greek bakers worked with wheat or barley flour, and they could add cheese, herbs, fruits, sesame seeds, nuts, and honey. Some cakes were flat and simple. Others were layered. Some were shaped for specific rituals. The idea that a sweeter baked food belonged to a special moment was already well established. The Greek names make this old world feel a little more real. A melatoessa was simply a honey cake. A plakus was a layered cheese pie or cake, sometimes flavored with fruits, nuts, or herbs. A pelanos was a sacrificial cake. During the festival of Artemis Munichia, held around the full moon of the Athenian month Munichion, roughly April 27th to 29th, worshippers offered amphiphon cakes topped with little lights. That image, a round cake with small flames on top, feels unexpectedly close to a modern birthday cake, even though the meaning was very different. By the time we reach Rome, the record becomes more exact because recipes begin to survive in writing. In the 2nd century BCE, Cato the Elder included recipes for several cakes in De Agricultura. One of them, libum, calls for 2 pounds of cheese, 1 pound of wheat flour or half a pound of fine flour, and 1 egg, baked slowly on leaves under a hot cover. Another, placenta, is much more elaborate. Layers of dough and cheese filling with 14 pounds of sheep's cheese and 4.5 pounds of honey, set on oiled bay leaves and baked slowly under a hot crock with coals around it. These are not modern cakes, but they are unmistakably part of the family. They are sweet, rich, ceremonial, and carefully designed. That is why the history of cake feels gradual instead of sudden. The word cake itself does not show up until the 13th century, from the Old Norse kaka, but the food is much older than the word. Long before English had a name for cake, people in Egypt, Greece, and Rome were already making sweet baked foods with grain, fat, cheese, fruit, and honey, and setting them aside for gods, guests, and feast days. So in its earliest forms, cake was heavier, rougher, and rarer than it is now. It belonged to a world where sweetness came from bees and dates, where flour was coarse, where ovens had hot spots, and where a richer bake might appear only at a festival or on a sacred day. The ancient version had the shape of cake's future, but not yet its softness. That softer world would need one ingredient, above all others, to begin changing everything. That ingredient was sugar. More exactly, it was sucrose, the same molecule whether it came from sugarcane or, later, sugar beet. For a very long time, though, most of the sugar that changed cake came from cane. The plant itself, Saccharum officinarum, was first domesticated in the region of New Guinea, then moved west across Asia over many centuries. In England, sugar was known by the 12th century, but it was not an everyday baking staple. It was treated more like a spice, a medicine, or a luxury. When refined sugar began to appear in Europe in the familiar cone-shaped sugar loaf form during the 1400s, it still had to be broken apart with special cutters before it could be measured into food. So at first, sugar did not create the everyday cake. It created the expensive cake. That mattered because cake was already linked with special occasions. Once sugar entered that world, it sharpened the difference between ordinary bread and celebratory baking. A loaf made with grain and yeast could feed a household. A sweetened cake announced that this meal was different. It used more labor, more fuel, more refinement, and ingredients that were harder to afford. In the 16th, 17th, and 18th centuries, the spread of cane sugar through European trade made that sweetness more visible, but it also tied baking to a harsh global system. Much of the sugar reaching Europe came from Caribbean plantations, worked by enslaved labor. The softness of cake had a very hard history behind it. As sugar became more available, the baked goods themselves began to change shape. Older sweet breads and fruit-rich loaves gradually moved towards something more recognizably like cake. You can see that shift clearly in one famous example: pound cake. By 1747, printed recipes in Britain described a cake made from 1 pound each of flour, butter, eggs, and sugar. That recipe is useful because it shows sugar no longer acting like a tiny luxury added at the edge. It now stood at the center of the formula, equal in weight to the flour itself. Cake was no longer only bread made richer. It was becoming its own thing, and sugar changed more than taste. In the mixing bowl, sugar crystals do physical work. When butter and sugar are beaten together, the sharp edges of the sugar crystals cut tiny pockets into the fat. Those little air spaces matter. In the oven, they fill with expanding gases, and help the cake rise. That means sugar is part of the structure, even before the batter is baked. It also changes the way the batter sets. Sugar competes with starch and proteins for water. Because of that, the starch in flour swells later, and the proteins in eggs firm up later too. This delay is useful. It gives the bubbles in the batter a little more time to expand before the cake becomes fixed in place. That is one reason a cake with enough sugar can feel fine crumbed and tender instead of tight and heavy. This is not a tiny effect. In test baking, when sugar is reduced too far, cakes often come out paler, drier, and less soft. One Nebraska baking guide puts a number on it. Cut sugar by more than 1/3, and you can lose noticeable tenderness, moisture, and browning. So when people say sugar is not just for sweetness, that is not a poetic phrase. It is a practical one. Sugar helps with water too. It is hygroscopic, which means it attracts and holds moisture. That helps cake stay soft for longer after baking. It also lowers water activity, which makes it a little harder for microbes to grow and helps extend shelf life. This is one reason a frosted supermarket cake can stay pleasant for days, while a plain low-sugar cake goes stale much faster. Then there is color. Part of the golden top of a cake comes from sugar browning at the surface. Part also comes from the Maillard reaction, where sugars and proteins react together under heat to create new color and aroma compounds. Either way, sugar helps produce the smell people recognize almost instantly: toasted, warm, sweet, and slightly buttery. It turns a pale batter into something that looks and smells finished. And as sugar became easier to buy in different grades, cake stopped belonging only to the highest tables. By 1700, England had sugar refineries, called sugar bakers, in cities from Plymouth to Glasgow. Not everyone could afford the whitest triple refined sugar, but people could also buy brown sugar or dark treacle. That widening range changed who cake was for. A highly decorated iced cake still signaled wealth, but sweet baking no longer belonged only to nobles and courts. It began to move into shops, kitchens, and family recipes. Once that happened, cakes became more theatrical too. Refined sugar made white icing, sugar paste, molded decorations, and smoother finishes possible. By the time of Queen Victoria's wedding in 1840, cake had become a public spectacle. Her wedding cake weighed about 300 pounds, stretched nearly 10 feet around, and was decorated with symbolic figures and heraldic details made from icing sugar. At that point, cake was no longer just baked, it was staged. And with sugar firmly in place, cake was now much closer to the form we know: softer, sweeter, more decorative, and more dependent on the hidden behavior of ingredients inside the batter. After all that history, it helps to come back to the bowl and look at the ingredient that sits there so quietly that it is easy to ignore. Flour does not usually get the glory. Nobody puts candles on a bag of flour. Nobody takes a photograph of it before a party. But in most cakes, flour is the part that gives everything else somewhere to go. Without it, cake batter would be sweet, rich and fragrant, but it would not hold a slice. It would not rise into shape and stay there. It would not have a crumb, which is the soft inside texture you see when a cake is cut. Most wheat flour is made mostly of starch, with a smaller amount of protein. A typical cake flour is roughly 70 to 75% starch, and often only about 7 to 9% protein. Bread flour, by contrast, is usually closer to 12 to 14% protein. Those numbers may look small, but in baking, they matter a great deal. The starch is what gives bulk. The proteins give strength. When flour is mixed with water or milk, two wheat proteins, glutenin and gliadin, begin to link together. When they join, they form gluten, which is the stretchy network that gives dough and batter some structure. Gluten is useful. Bread depends on it. A loaf of bread needs enough strength to trap gas, hold its shape, and survive kneading, rising, and slicing. Cake wants less of that strength. A cake should usually feel tender, not chewy. It should break apart easily under a fork. That is why many cake recipes prefer cake flour, which is milled from softer wheat and has less protein than bread flour. Less protein means less gluten can form. Less gluten means the crumb stays finer and softer. That difference is easy to picture in the kitchen. If someone bakes a yellow layer cake with bread flour instead of cake flour, the cake will usually rise in a rougher way, feel firmer in the bite, and sometimes pull into long, slightly rubbery strands when torn. The same recipe made with cake flour is more likely to produce a pale, even crumb, with very small air pockets. The kind of wheat matters too. In the United States, softer flours often come from soft red winter wheat or other low-protein wheats, while stronger bread flours often use hard red spring or hard red winter wheat. Even before any other ingredient is added, the grain itself has already nudged the cake in one direction or another. Then heat begins to do its work. As the batter warms in the oven, the starch granules in the flour absorb water and swell. This process is called gelatinization, which simply means the starch softens, swells, and thickens as it heats. For wheat starch, that usually begins somewhere around 60 to 70 degrees Celsius, or about 140 to 158 degrees Fahrenheit, though the exact point depends on sugar, fat, and moisture. Before that moment, the batter is loose and temporary. After it, the inside begins to set. This is one of the quiet miracles of cake. A pourable batter goes into the oven. 20 or 30 minutes later, it can be lifted out as something that holds together in slices. Part of that change comes from egg proteins firming up, but a very large part comes from flour starch absorbing liquid and turning the batter from a fluid system into a soft solid. Flour also affects color. Cake flour is often more finely milled and sometimes bleached, which makes it appear whiter and helps create a lighter colored crumb. That is one reason an angel food cake or a classic white birthday cake can look almost snowy inside. A flour with more bran or stronger pigments will darken the crumb and make the texture feel a little more rustic. Even a small shift in flour can change whether a cake looks delicate or hearty. Density changes too. A high-protein flour can make a cake more stable, which sounds good, but that extra stability often comes at the cost of tenderness. A low-protein flour gives a softer result, but if the recipe goes too far in that direction, the cake may become fragile and collapse more easily. So flour is always helping the baker balance two needs at once: softness and support. That balance shows up in many familiar cakes. A chiffon cake needs enough structure to rise tall and stay lifted, but it still has to feel light. A pound cake can handle a slightly stronger flour because it is meant to be denser and more solid. A sponge cake depends on very careful structure because much of its lift comes from air trapped in beaten eggs. In each case, flour is doing the quiet work of deciding how much the cake can hold, how cleanly it can slice, and how gently it can break apart in the mouth. So flour is the skeleton of cake, built mostly from starch and held together by proteins. It gives the batter shape, helps it set in the oven, and decides a surprising amount about texture, color, and weight. But a skeleton alone would make for something dry, plain, and a little severe. Cake needs another ingredient to bind, lift, and soften that framework from within. That ingredient is the egg. A single large chicken egg, the kind used in most baking recipes, weighs about 50 grams, or a little less than 2 ounces. It does not look like much on the counter. But inside that shell is a very useful system. About 3/4 water, some fat, and a group of proteins that can thicken, hold air, and firm up with heat. In cake, that makes eggs one of the hardest working ingredients in the bowl. They do several jobs at once. The first job is simple but important. Eggs help hold very different ingredients together. Cake batter usually contains water from milk or eggs, and fat from butter or oil. Water and fat do not naturally stay mixed for long. If left alone, they separate, the way oil floats on top of soup. Egg yolks help prevent that. They do this because yolks contain lecithin, a natural emulsifier. An emulsifier is a substance that helps fat and water stay mixed instead of breaking apart. Lecithin acts like a tiny bridge. One end is comfortable with water, and the other is comfortable with fat. So when eggs are beaten into a batter, the yolks help spread the fat more evenly through the liquid. That leads to a smoother batter, a finer crumb, and a cake that rises more evenly. You can sometimes see the difference with your eyes. A batter with enough egg yolk often looks glossy and creamy, almost like it has been polished. A batter without enough emulsifying power can look slightly curdled or grainy, especially if butter was added while too cold or too fast. Eggs also bind. That means they help separate ingredients behave like one mixture. Flour, sugar, fat, and liquid each want to do their own thing. Eggs help turn that loose collection into something more stable. This is one reason many classic cake recipes use 2 to 4 eggs for a standard 8 or 9-inch layer cake. The eggs are not there only for flavor. They are part of the framework. Then the heat of the oven changes them again. As a cake bakes, the proteins in the eggs begin to unfold and connect to one another. This process is called coagulation, which simply means the proteins firm up into a network. It is the same reason a raw egg white turns solid when cooked in a frying pan. In cake, that setting happens more gently because the proteins are spread through batter with sugar, flour, and fat. Different egg proteins set at slightly different temperatures. Egg whites begin to thicken in the range of about 60 to 65 degrees Celsius, or 140 to 149 degrees Fahrenheit, and yolks begin thickening a little later, often around 65 to 70 degrees Celsius, or 149 to 158 degrees Fahrenheit. In a cake, sugar delays this process somewhat, which is useful. It gives the batter more time to rise before the structure becomes fixed. That rising brings us to another major job eggs do. They trap air. When eggs are beaten, especially whites, they can form a foam. A foam is just a network of proteins holding tiny bubbles of air. Each bubble is small, but together they can change the whole texture of a cake. In sponge cakes, Genoese, angel food cakes, and chiffons, this trapped air is one of the main lifting forces. There may be little or no baking powder at all. Instead, the volume comes from eggs that have been whipped until they expand. An egg white can increase many times in volume when beaten properly. At first, it looks loose and bubbly. Then it becomes white and foamy. Then soft peaks form. Then firmer peaks. At that stage, millions of tiny air bubbles are being held by stretched egg proteins. In the oven, those bubbles expand as the air warms and water turns to steam. If the batter is handled gently, the cake rises around them. This is why sponge cakes can feel almost weightless. They are built partly from air that was trapped before baking even began. Yolks and whites do not behave the same way, and bakers use that difference on purpose. The yolk contains most of the egg's fat, along with lecithin, flavor compounds, and pigments called xanthophylls, which give many cakes their warm yellow color. A butter cake made with extra yolks often looks deeper gold and tastes richer. The crumb may seem smoother and softer too, because the added fat interferes with too much gluten formation. The white, by contrast, is mostly water and protein. It has almost no fat. That makes it excellent for foaming. Fat weakens foam, which is why even a small smear of yolk in egg whites can make them harder to whip. Recipes that want a very light, airy texture often lean heavily on whites for exactly that reason. You can feel the contrast in familiar cakes. A yellow birthday cake gets much of its richness and color from yolks. An angel food cake uses only whites, which is why it comes out pale, springy, and very light. A chiffon cake uses both. Yolks for richness, whites for lift. It is almost like borrowing the strengths of two different ingredients, even though they came from the same shell. So eggs are doing several quiet jobs at once. They help fat and water stay together. They hold the batter in a more stable form. Their proteins set in the oven and strengthen the cake. And when beaten, they carry air into the mixture, giving lift that can make the difference between a heavy cake and a delicate one. If flour builds the framework and eggs help hold and support it, the next ingredient changes how that structure feels, making it softer, shorter, and far less likely to turn tough. That softening ingredient is fat. If flour gives cake its frame, and eggs help hold that frame together, fat changes the feel of it. It takes something that might otherwise bake up firm and a little plain, and turns it into something gentler. In baking, that difference is easy to notice. A lean batter with very little fat can feel closer to bread. A richer batter feels softer, shorter, and easier to bite through. Bakers use the word short in a special way here. It does not mean small. It means crumbly or tender, the opposite of stretchy. The word shortening comes from that idea. Fat shortens gluten's strands, cutting down the long elastic network that flour and water would otherwise build. This begins the moment fat meets flour. Flour contains those two important wheat proteins, glutenin and gliadin, which join with water to form gluten. But if butter, oil, or another fat coats some of the flour first, less water can reach those proteins. That means less gluten forms. The batter stays softer and less elastic. Instead of acting like bread dough, which can be kneaded and stretched, cake batter stays tender. You can picture it like this. Flour wants to build a tight net. Fat gets in the way and snips some of the threads before they fully connect. That is why recipes for cakes often include a substantial amount of fat. A classic butter cake might use about 200 to 230 grams of butter for 250 grams of flour, roughly equal to 1 cup of butter and 2 cups of flour. In a pound cake, the old formula went even further, calling for equal weights of flour, sugar, butter, and eggs. That is a rich mixture, and the richness shows up in the final texture. Butter is one of the most common cake fats, and it brings more than softness. Standard butter is about 80% fat, with the rest mostly water and a small amount of milk solids. Those milk solids are useful because they carry flavor and help with browning. They are part of why butter cakes smell warm and round, in a way that is hard to mistake. Butter also behaves differently depending on temperature. At a cool room temperature, around 20 to 22 degrees Celsius, or 68 to 72 degrees Fahrenheit, softened butter can trap air when beaten with sugar. That is the creaming method, and it helps create a light crumb. Once the cake cools after baking, the butter firms up again. That is why a butter cake taken from the refrigerator feels slightly denser and more solid than the same cake left on the counter for an hour. Oil behaves differently because it is liquid at room temperature. A cake made with vegetable oil, sunflower oil, or canola oil often feels moister for longer. Since the oil never firms up the way butter does, the crumb stays soft even when the cake is cool. This is one reason carrot cakes, many chocolate cakes, and some sheet cakes use oil. An oil-based cake can stay tender for a day or two in a way a butter cake sometimes does not. The trade-off is flavor. Most neutral oils have very little aroma of their own. Butter carries hundreds of flavor compounds, including diacetyl, which gives a buttery smell. Oil usually cannot match that, so a butter cake may smell richer, while an oil cake may stay soft longer. Then there is shortening, a more processed fat that is usually 100% fat and solid at room temperature. Because it contains no water, it can make a cake very tender and stable. It is often used in frostings and commercial baking because it holds shape well, especially in warm rooms. But many people notice that shortening feels different in the mouth. It can seem smooth, but also a little flatter in flavor than butter. So different fats shape the cake in different ways. They change the size of the crumb, the softness of the bite, the way the cake smells, the way it melts on the tongue, and even how it feels a few hours after baking. By the time fat has done its work, the structure is no longer severe. It has become tender enough to feel like cake. And once that tenderness appears, sweetness has even more to do than simply make the whole thing taste pleasant. And that extra work begins in the bowl, long before anyone takes a bite. Sugar certainly makes cake sweet, but inside the batter it behaves like a tool. In many layer cakes, the amount is striking. A basic yellow cake might use 300 to 400 grams of sugar with 250 grams of flour, which means the sugar can weigh as much as, or even more than, the flour. That is not just there for taste. If cake only needed a little sweetness, bakers would use far less. One of sugar's most important jobs is managing water. Sugar is hygroscopic, which means it attracts and holds onto water. That matters because cake goes stale when moisture shifts and the crumb becomes firmer and drier. With enough sugar in the batter, some of that water stays tied up for longer. The cake stays softer. This is easy to notice in real life. A plain sponge with very little sugar can feel dry by the next day. A frosted birthday cake with a higher sugar content often stays soft for 2 or even 3 days if covered well. Sugar also changes when the cake sets. Flour starch needs water and heat to swell and firm up. Egg proteins need heat to unfold and connect. Sugar gets in the way of both processes just enough to help. It competes for some of the water, so the starch swells a little later, and the proteins firm a little more slowly. That delay gives the bubbles in the batter extra time to expand before the structure locks into place. The result is usually a finer, more tender crumb. This is one reason reducing sugar too much can cause trouble. A cake made with only half its usual sugar often bakes up shorter, firmer, and less golden. It may still taste acceptable, but the texture changes. The crumb gets tighter. The surface may look pale. The whole cake can seem less like cake and more like a sweet bread. Sugar helps create lift in another way too, especially with butter cakes. During creaming, the sharp edges of sugar crystals cut tiny air pockets into softened butter. Those pockets trap air. In the oven, that air expands, helping the cake rise. Fine granulated sugar works well for this because the crystals are small enough to mix evenly, but still sharp enough to do that cutting work. Powdered sugar, by contrast, behaves differently because it contains much smaller particles and often a little starch. Then there is the top of the cake, where sugar helps create one of the most familiar signs of doneness: color. As the surface heats up and loses moisture, sugars begin to brown. Some of that browning is caramelization, which means sugar molecules break down under heat and form new flavors and colors. Some also comes from the Maillard reaction, a process where sugars react with proteins and create toasted, nutty, warm-smelling compounds. That is why the crust of a cake can smell a little like toffee, vanilla, or toasted milk, even before frosting goes on. Different sugars shape that result in different ways. White granulated sugar is mostly pure sucrose. It gives clean sweetness and a light-colored crumb. Brown sugar is white sugar with molasses mixed in, either left in naturally or added back later. Molasses contains minerals and darker flavor compounds, so brown sugar brings notes that many people describe as deeper, warmer, or slightly caramel-like. Because brown sugar also holds more moisture, cakes made with it can feel softer and denser. That is why many ginger cakes, spice cakes, and some chocolate cakes use brown sugar. It suits those darker flavors. Liquid sweeteners change things again. Honey, maple syrup, corn syrup, or golden syrup all add water along with sugar, so they can make a batter looser. They also contain different kinds of sugars. Honey, for example, has a lot of fructose, which is sweeter than sucrose and browns readily. That can make a honey cake darker and more moist, but also a little heavier if the recipe is not adjusted. A batter with syrup often needs less other liquid to stay balanced. So sugar is not just the pleasant part. It controls moisture, delays structure, helps trap air, deepens aroma, and changes color. It can make a cake paler or darker, lighter or denser, cleaner in flavor or more complex. By now, the batter has flour for structure, eggs for support, fat for tenderness, and sugar doing several quiet jobs at once. What it still needs is the right amount of liquid to bring all those parts together and turn them into something smooth, workable, and ready to rise. And those parts only become a batter once liquid enters the picture. Liquid is easy to overlook because it seems so ordinary. A splash of milk, a spoonful of yogurt, a little coffee, maybe some sour cream. Compared with flour or sugar, it does not feel dramatic. But without liquid, cake never really begins. Dry ingredients can be measured into a bowl, but they remain separate until water gives them a way to interact. That matters right away with flour. Flour needs moisture before it can do any of its real work. Starch granules have to absorb water before they can swell in the oven. The proteins in flour need water before they can link into even a small amount of structure. Sugar also needs liquid if it is going to dissolve smoothly instead of staying sandy. So one quiet role of liquid is simply this. It turns a pile of ingredients into a single system. In many home cakes, that liquid begins with milk. Whole milk is mostly water, about 87%. But the remaining part matters too. It carries lactose, which is milk sugar, along with proteins like casein and whey, plus a small amount of fat if it is not skim. All of those change the finished cake. The water hydrates the flour. The milk proteins support browning. The lactose helps the crust color more deeply because it takes part in heat-driven browning reactions. And the bit of fat adds softness. That is one reason a cake made with milk often looks slightly more golden than a cake made with plain water. Even the difference between whole milk and skim milk can be felt. Whole milk with around 3.25% fat usually gives a slightly fuller mouthfeel. Skim milk can still work, but the cake may seem a little leaner. Evaporated milk, which has had about 60% of its water removed, gives a richer effect still because it brings more milk solids into the batter. Then there are acidic liquids, which do something especially useful. Buttermilk, for example, is usually around a pH of 4.4 to 4.8, which means it is noticeably acidic. That acid can weaken gluten a little, helping the crumb stay tender. It also reacts with baking soda, which is sodium bicarbonate. When baking soda meets acid and moisture, it releases carbon dioxide gas. Those gas bubbles help lift the cake. This is why classic red velvet cake, old-fashioned chocolate cakes, and many southern layer cakes often call for buttermilk and baking soda together. It is a partnership, not just a flavor choice. Yogurt works in a similar way. Plain yogurt is also acidic, and because it is thicker than milk, it can add both tenderness and body. A yogurt cake often feels moist and slightly dense in a pleasant way, with a close crumb rather than a wide open one. Sour cream goes even further. It is thicker, richer, and higher in fat than milk or buttermilk, often around 18 to 20% fat. That richness can produce a velvety crumb and help a cake stay soft for longer. A coffee cake or pound cake made with sour cream often has a very fine interior texture, almost smooth enough to seem creamy. Other liquids can change flavor just as much as structure. Coffee is a good example. A half cup of brewed coffee in a chocolate cake does not usually make the cake taste like a cup of coffee. Instead, it deepens the chocolate, making it seem darker and fuller. Orange juice adds water, sugar, and acid, along with a clear citrus aroma. Lemon juice is more sharply acidic and is often used in smaller amounts for brightness. Even plain hot water can matter, especially in cocoa-based batters, where it helps bloom the cocoa and dissolve ingredients evenly. So liquid is not just filler. It hydrates flour, dissolves sugar, helps ingredients merge, carries flavor, and can change tenderness, browning, and density depending on what form it takes. By this point, the batter has all its main building materials in place. What remains is the question that decides whether it will bake up light and airy or stay heavy in the pan. The answer is leavening. Leavening is the part of baking where stillness turns into expansion. A batter that looks smooth and quiet in the bowl begins to swell in the oven. The surface rounds upward. The crumb opens. A layer cake that began at maybe 3 centimeters or a little over 1 inch of batter in the pan can rise to twice that height or more. All of that depends on gas. Cake rises because tiny bubbles inside the batter grow larger. Those bubbles can come from carbon dioxide, from air, from steam, or from all three at once. Carbon dioxide is a gas made during chemical reactions. Air is already present if eggs or butter have been beaten well. Steam appears when water in the batter gets hot enough to turn into vapor. The important thing is not just making gas, but trapping it long enough for the structure to set around it. That is why cake and bread feel so different. Bread often depends on yeast, a living microorganism that ferments sugars over 1 or 2 hours, sometimes longer, and produces carbon dioxide slowly. Cake usually works faster. Most cakes rise through chemical leaveners, meaning ingredients that create gas as soon as they get wet, hot, or both. The most common one is baking powder. Baking powder is basically a small built-in reaction system. It usually contains baking soda, 1 or more dry acids, and starch to keep everything stable in the container. Once moisture reaches it, the acid and soda begin reacting. That reaction produces carbon dioxide gas. In many modern baking powders, part of the reaction starts in the bowl, and part happens later in the oven. That is called double-acting baking powder. The first stage begins when the batter is mixed. The second begins when heat increases in the oven. That 2-step timing is useful because it gives a cake 2 chances to rise. A standard cake recipe might use 1 to 1.5 teaspoons of baking powder per cup of flour, though recipes vary. Too little, and the cake comes out low and close textured. Too much, and the bubbles can grow too fast, then collapse before the crumb has time to set. The result can be a cake that rises beautifully for a few minutes, then sinks in the center. Baking soda is simpler but fussier. Baking soda is pure sodium bicarbonate. It needs acid to react properly. If there is no acid in the batter, it will not produce enough gas at the right time, and it can leave behind a slightly soapy or bitter taste. That is why baking soda often appears with ingredients like buttermilk, yogurt, brown sugar, lemon juice, or natural cocoa powder, which is more acidic than the Dutch processed kind. A classic example is red velvet cake. Many older versions use buttermilk, a little vinegar, and baking soda. Those acids wake up the soda and help create a soft, lifted crumb. But chemical leaveners are not the whole story. Air can be worked into batter before baking even begins. When softened butter and sugar are creamed together for 3 to 5 minutes, thousands of tiny air pockets form. When eggs are whipped, especially whites, they can hold even more. In a sponge cake, that trapped air is a major source of lift. In an angel food cake, whipped egg whites do nearly all the work. In a chiffon cake, whipped whites and baking powder work together. Then the oven takes over. As the batter heats, the gases already inside expand. Any carbon dioxide from baking powder or soda grows larger. Water turns to steam at 100 degrees Celsius or 212 degrees Fahrenheit, though pressure inside the batter affects exactly when and how it appears. Steam is powerful because water expands dramatically when it becomes vapor. That extra push helps open the crumb during the first part of baking, sometimes called oven spring, the brief period when the cake rises fastest before the structure sets. So leavening is really a chain of events. Air added during mixing, gas released by chemical reactions, steam generated by heat, and a batter strong enough to hold all of it for long enough. That gives the cake its chance. But a chance is not the same thing as a result. Whether those bubbles stay small and even, or become coarse, uneven, or lost entirely, depends very much on how the batter is mixed. That part can look simple from the outside. A person stands at a counter, turns on a mixer, scrapes a bowl, and stops. But mixing is one of the most decisive moments in the whole life of a cake. It is where texture begins long before the oven has a chance to finish anything. Take the creaming method, one of the classic ways to start a butter cake. When softened butter and sugar are beaten together, usually for about 3 to 5 minutes on medium speed, the sugar crystals cut tiny pockets into the butter. Those pockets trap air. Not giant bubbles, just very small ones, scattered through the fat. Later, in the oven, those little pockets give expanding gases somewhere to start. That is one reason a properly creamed cake can have such a fine, even crumb. You can often see the change happen. At the beginning, the butter looks yellow, dense, and a little greasy. A few minutes later, it becomes paler and fluffier because it now contains thousands of tiny air spaces. If the butter is too cold, around refrigerator temperature, it will not trap air well. If it is too warm, almost melting, it turns slick and heavy. That is why many recipes quietly depend on butter being near 20 to 22 degrees Celsius, or 68 to 72 degrees Fahrenheit. Soft enough to dent with a finger, but not shiny or collapsed. Then eggs are added, often one at a time. That slow pace matters. Add them too quickly, and the mixture can curdle, which means the fat and liquid separate into a grainy-looking mess. It may still bake, but the texture is usually not as smooth. Other cakes rely less on creaming and more on whipped eggs. In a sponge cake or chiffon, eggs may be beaten for 5 to 10 minutes, depending on the method, until they reach what bakers call the ribbon stage. That means the mixture becomes thick enough that when it falls from the whisk, It leaves a ribbon-shaped trail on the surface for a few seconds before sinking back in. That thickness tells you air has been worked in. Once that air is there, the next job is not to lose it. That is where folding comes in. Folding is a gentler way of combining ingredients. Instead of stirring in circles or beating with force, a spatula is pulled down through the middle of the bowl, swept across the bottom, and lifted up the side, turning the batter over itself. It is slow, but it protects the foam. In a chiffon or genoise, too much rough mixing can knock out the air that took several minutes to build. At the other extreme is overmixing. Once flour and liquid meet, gluten begins to form. That is useful up to a point, but if the batter is beaten too long after the flour goes in, the cake can become tougher and less tender. Sometimes it also develops tunnels, which are long, narrow holes running through the crumb. They look almost like tiny caves or channels inside the slice. Those tunnels form when a batter becomes too elastic and strong, so the expanding gases push through it unevenly instead of lifting it gently. Different mixing methods lead to different kinds of cakes because they arrange fat, air, and flour differently. A one-bowl or all-in method is exactly what it sounds like. Many ingredients go in together and are mixed in a shorter, simpler process. It is convenient and common in home baking, especially for oil cakes or quick sheet cakes. The crumb may be slightly less delicate than a careful cream cake, but it can still be very good. Reverse creaming works the other way around from the old butter first method. In that approach, softened butter is mixed into the flour before much liquid is added. That coats the flour with fat early and limits gluten formation from the start. The result is often a very fine, tight, velvety crumb, the kind many bakery-style layer cakes aim for. The whipped egg method, used in sponge cakes, builds structure from air beaten into eggs rather than mostly from chemical leaveners. That gives a lighter, springier texture. So by the time mixing is done, the batter is no longer just ingredients sharing a bowl. It has become a balanced system of air bubbles, dissolved sugar, hydrated flour, fat droplets, and liquid, all arranged in a very particular way. And that balance, once created, is surprisingly delicate. That delicacy is easier to understand once you stop thinking of batter as a simple mixture and start seeing it as a temporary structure. In the bowl, cake batter is not fully solid, and it is not truly liquid either. It is a suspension, which means tiny bits of one thing are held throughout another thing without fully disappearing. Flour particles are suspended in water and fat. Sugar is partly dissolved. Fat is broken into droplets. Air is trapped as bubbles. If cocoa is present, it joins that system too. Even salt and baking powder are spread through it in very small amounts, doing quiet work out of sight. A finished batter may look smooth, but on a small scale, it is crowded and busy. In one spoonful of yellow cake batter, there are starch granules from the flour, proteins from flour and eggs, water from milk and eggs, fat from butter or oil, and thousands of bubbles of different sizes. Some of those bubbles came from creaming. Some came from whipped eggs. Some may already be forming from baking powder reacting with moisture. All of those parts have to stay in balance long enough to reach the oven. That is why batter is temporary. Nothing in it has fully set yet. The starch has not gelatinized, which means it has not swollen and firmed with heat. The egg proteins have not coagulated, which means they have not formed the firm network that helps the cake hold shape. The bubbles are there, but they are fragile. If the batter is jarred, overhandled, or left waiting too long, some of that trapped gas can escape before it ever has a chance to lift the cake. The fat and water are also in a temporary peace. A cake batter is usually an emulsion, which is a mixture where tiny droplets of fat are spread through water, or water through fat, without fully separating. Egg yolks help hold that emulsion together because of lecithin. But the emulsion is not invincible. If the ingredients are too cold, too warm, or added in the wrong order, the batter can break. When that happens, it may look curdled, greasy, or grainy. A broken batter sometimes still bakes into something decent, but often the crumb comes out less even. Thickness matters just as much. A batter that is too loose may rise quickly and then sink because it does not have enough body to support expanding bubbles. A batter that is too stiff may hold its shape in the bowl, but then struggle to rise well because the bubbles cannot expand easily through it. You can often see the difference with a spatula. A loose batter may pour like heavy cream. A stiffer butter cake batter may fall in thick ribbons. A muffin-like batter may need to be spooned. Each style works best within a certain range. This is one reason recipe ratios matter so much. Too much liquid for the amount of flour, and the center may collapse or remain gummy. Too little liquid, and the cake may bake up dry, peaked, or dense. Even a change of 2 or 3 tablespoons can be enough to noticeably alter the texture of a single layer cake. Time matters too, sometimes more than people expect. A butter cake made with double-acting baking powder has a little flexibility, but even then it is best not to sit around for half an hour after mixing. Some of the gas-producing reaction has already begun. A whipped sponge is even more urgent. Leave a Genoese or chiffon batter waiting too long, and the foam slowly deflates. The bubbles merge, rise, and pop. Volume is lost without making any sound at all. So in the bowl, batter is all possibility. It is structured, but not fixed. Lift is present, but not secure. Moisture is in place, but not yet transformed. The ingredients are cooperating, but only for a while. And that brief, unstable state is exactly what makes the next step so important. Because the bowl can only hold potential. The oven is where that potential becomes cake. And once the pan slides into the oven, that change begins almost at once. A cake usually bakes somewhere between 325 and 350 degrees Fahrenheit, or about 163 to 177 degrees Celsius. At that point, the batter is still soft enough to move, and for the first several minutes, it becomes even more active. The tiny bubbles already trapped inside begin to expand as they warm. Any carbon dioxide released by baking powder or baking soda pushes outward. Water in the batter starts turning into steam. Steam is powerful because when liquid water becomes vapor, it takes up far more space. That extra volume helps lift the batter from within. This early period is when the cake rises fastest. If you have ever looked through the oven window around the 10-minute mark, you may have seen the surface slowly doming upward. That is the batter still flexible enough to stretch while the gases inside grow larger. In a well-made cake, those bubbles stay small and fairly even. In a poorly mixed one, they may gather into larger pockets and create a rough crumb or a peaked top. But the batter cannot stay fluid forever. Heat keeps moving inward, and with that heat come the changes that make the rise permanent. The proteins in eggs begin to coagulate, which means they unfold and connect into a firmer network. In simple terms, they go from loose and slippery to set and supportive, much the way a raw egg becomes solid in a pan. At the same time, the starch in the flour begins to gelatinize. That means the starch granules absorb water, swell, and thicken. Together, those two changes turn a pourable batter into a soft solid. This usually begins when the center of the cake reaches roughly 180 to 200 degrees Fahrenheit, or about 82 to 93 degrees Celsius. Before that point, the structure is still forming. After that point, the shape becomes harder to change. The cake stops rising because the walls around the bubbles have set in place. Other changes are happening too. Butter melts early in the process, usually between about 90 and 95 degrees Fahrenheit, depending on its exact makeup. Oil, which was already liquid, moves more freely through the batter as it heats. Sugar dissolves further into the moisture that remains, helping keep the crumbs soft. Water shifts constantly, moving from the center toward the surface, where some of it escapes as steam. That movement of moisture is one reason cakes do not bake evenly from edge to center. The outer part of the cake is closer to the hot metal pan and the oven air, so it heats first. The center is protected by the batter around it, so it warms more slowly. In a standard 9-inch round pan, the edges may be set while the middle is still rising. In a deeper pan, that difference becomes even greater. A thick loaf cake may need 50 to 70 minutes, while thinner cake layers may finish in 25 to 35 minutes because heat has less distance to travel. Oven temperature matters for the same reason. If the oven is too hot, say 375 degrees Fahrenheit instead of 350, the outside can set and brown before the center has fully expanded. The result may be a cake with a cracked dome, dry edges, or an underbaked middle. If the oven is too cool, the cake may rise slowly, lose some of its lift, and come out pale or heavy. Pan color matters too. Dark metal absorbs more heat than shiny aluminum, so a cake in a dark pan often browns faster at the edges. By the end of baking, the batter has passed through a set of changes it cannot undo. The bubbles have expanded, the proteins have set, the starch has thickened, the fat has melted into the crumb, the moisture has shifted. What went in as a temporary system comes out as a sliceable cake. And once that structure is in place, another part of the experience begins to matter just as much. The kitchen starts to smell warm and sweet, and the surface begins to take on the color people recognize before they even cut the first slice. That warm smell is one of the most recognizable signals in a kitchen. Long before a cake is sliced, or frosted, or set on a plate, the air begins to change. Somewhere around the middle of baking, often after 15 to 20 minutes for a standard layer cake, the kitchen starts to fill with a smell that is sweet, warm, and almost impossible to mistake. People usually call it simply the smell of cake, but that smell is really a crowd of smaller chemical events happening at the surface and just beneath it. A good part of that change comes from browning. As the cake bakes, the outside dries more quickly than the center because it is exposed to hot oven air and the hot metal of the pan. Once the surface loses enough moisture, its temperature can climb above the boiling point of water and move into the range where browning reactions speed up. Two of the main ones are caramelization and the Maillard reaction. Caramelization is what happens when sugars break down under heat and form new compounds with deeper color and flavor. That process tends to happen at fairly high temperatures, often above 320 degrees Fahrenheit, or about 160 degrees Celsius, though the exact point depends on which sugar is present and how much water remains. It creates notes that people describe as toffee-like, buttery, or slightly nutty. The Maillard reaction is a little different. It happens when sugars react with proteins under heat. In cake, that means sugars meeting proteins from flour, eggs, or milk. This reaction can begin at lower temperatures than caramelization and produces a wide range of brown colors and toasted aromas. It is the same family of reaction that helps brown bread crust, roasted coffee, and seared meat. Though in cake, the flavors are gentler and sweeter. Which reaction matters more depends on the batter. A cake made with milk has more protein and lactose at the surface, so Maillard browning plays a larger role. A cake with a high sugar content and a dry top may lean more toward caramelization. A honey cake browns differently from a white sponge because fructose, one of the main sugars in honey, browns more readily than plain table sugar. Brown sugar changes things too, because the molasses in it carries darker flavor compounds from the start. As these reactions unfold, they create not one smell, but hundreds of aroma compounds. Some are familiar enough to name. Vanillin, the main aroma compound in vanilla, gives that soft, sweet bakery note many people associate with yellow cake. Diacetyl, found in butter, adds a buttery smell. Cocoa brings its own complex mix, including roasted and earthy notes, formed during the fermentation and roasting of cacao beans. Toasted sugar adds warmer notes that can suggest caramel, butterscotch, or even light coffee. Together, those compounds blend into something most people do not break apart analytically. They just recognize it. Cake smell. That recognition matters because smell is a huge part of flavor. In fact, much of what people think of as taste is actually aroma reaching the nose from the mouth while eating. The tongue can detect a few basic things like sweet, sour, salty, bitter, and savory. But the nose handles the finer details. That is why cake can already seem rich before it is tasted. The brain has started building the experience from smell alone. This is also why warm cake smells stronger than cold cake. Heat helps aroma molecules move through the air more easily. A freshly baked vanilla cake cooling on the counter gives off a stronger signal than the same cake 2 hours later, even if the ingredients are identical, and the smell itself carries meaning. Warm butter, sugar, vanilla, and cocoa are not just chemical signals. For many people, they are tied to birthdays, school bake sales, holidays, and ordinary afternoons in kitchens with the oven on. The smell tells you not only that something is baking, but that it is nearly ready. Still, nearly ready is not the same as finished. The cake may smell done, and the top may be golden, but inside it is still settling, releasing steam, and moving toward its final texture. Cooling has its own quiet science. And that science begins the moment the cake leaves the oven. It is easy to imagine baking as a process with a clear finish line. The timer rings, the pan comes out, the cake is done. But in reality, the cake keeps changing for quite a while after it meets the cooler air of the kitchen. Part of that is because of residual heat, which simply means the heat still trapped inside the cake. A standard 9-inch layer cake may come out of the oven with its center still close to 200 degrees Fahrenheit, or about 93 degrees Celsius. That is hot enough for cooking to continue even after the pan is on a rack. The outer edges begin cooling right away, but the center stays warm longer, so for several minutes the cake is still settling into itself. Steam is part of that settling. During baking, water in the batter turned to vapor and pushed outward through the crumb. Once the cake leaves the oven, some of that steam escapes into the room, but some stays inside and begins to redistribute. In simple terms, moisture moves from the hotter center toward the cooler outer parts. That helps even out the texture. A cake that feels almost too soft in the middle when it first comes out can become firmer and more sliceable after 20 to 30 minutes of cooling. The crumb changes too. While the cake is hottest, its internal structure is still delicate. The starches have swollen, the egg proteins have set, and the fat is still fully melted. That means the cake can hold its shape, but only just. If it is handled roughly at that moment, the crumb may compress, tear, or collapse. This is why many recipes tell bakers to let a cake rest in its pan for about 10 minutes before turning it out. That short wait matters. If the cake is removed too early, while it is still very hot and fragile, it can break across the middle or leave chunks behind in the pan. The structure has not yet firmed enough to survive being flipped or lifted. A chiffon cake is even more delicate and often has to cool upside down in its tube pan, so it does not sink under its own weight. But leaving a cake in the pan too long has its own problems. A hot cake gives off steam. If that steam is trapped by the sides and bottom of the pan for too long, moisture can condense and collect around the edges. The result can be a damp, slightly sticky outer layer. In some cases, especially with loaf cakes or very moist batters, the bottom can become almost soggy. That is why the usual advice is not immediate removal and not endless waiting, but a middle path, a brief rest, then transfer to a wire rack so air can reach the cake from below as well as above. The wire rack helps more than people realize. Without it, the bottom of the pan or plate holds in heat and slows evaporation. With it, warm air can circulate and moisture can leave more evenly. Cooling also decides whether frosting will behave. Buttercream begins softening quickly in warmth because butter starts to lose firmness well below body temperature. Whipped cream is even less stable. Ganache, made from chocolate and cream, can turn loose and shiny if spread over a cake that is still warm. Cream cheese frosting may slide. Jam fillings can thin out. Even a simple dusting of powdered sugar can melt into the surface instead of sitting lightly on top. That is why many bakers wait until a cake has cooled fully, often 1 to 2 hours for standard layers, before decorating. Some even chill the layers briefly so crumbs stay in place during frosting. So cooling is not a pause between important stages. It is one of the important stages. Heat is still moving. Steam is still redistributing. the crumb is still settling from fragile to stable, and the cake is becoming ready for whatever comes next. Because once it has cooled properly, another kind of structure can begin to take shape around it. Frosting, filling, and finish. That outer structure has its own quiet science. A plain cake can be good on its own, but frosting and filling change how the whole thing is felt, not just how it tastes. They affect softness, temperature, sweetness, weight, and even the way a fork moves through a slice. In most cases, frosting is some balance of sugar, fat, air, and sometimes water or dairy. Change the balance, and the frosting behaves differently on the cake and in the mouth. Take buttercream, one of the most common examples. An American-style buttercream is usually made from butter and powdered sugar, sometimes with a little milk or cream, vanilla and salt. Powdered sugar matters because it dissolves more easily than granulated sugar and often contains a little starch, which helps keep it from clumping. A typical batch for an 8 or 9-inch layer cake might use 225 grams or 1 cup of butter and 450 to 500 grams, or about 4 cups of powdered sugar. That gives a frosting that is sweet, spreadable, and stable enough to hold soft ridges from a spatula. But buttercream changes fast with temperature. Butter begins to soften well below body temperature, which is why a buttercream cake feels firmer at 65 degrees Fahrenheit than it does at 75. On a warm day, pipe swirls can slowly relax. In the refrigerator, the same frosting firms almost like soft clay and needs time to become creamy again. Whipped cream behaves differently because it is built from cream rather than solid fat. Heavy cream, usually around 36% fat, can trap air when beaten cold. That creates a light foam, but it is fragile. Leave a whipped cream cake in a warm room too long and the foam can collapse, releasing liquid. That is why many bakery cakes filled with whipped cream need refrigeration and are best eaten the same day. Ganache is another system entirely. It is usually just chocolate and cream, often in a ratio close to 1:1 for a soft glaze, or 2 parts chocolate to 1 part cream for a firmer filling. The cocoa butter in chocolate firms as it cools, so ganache can pour when warm, spread when slightly cooled, and set into something sliceable later on. A chocolate drip cake depends on hitting that brief middle stage, fluid enough to flow down the sides, but not so hot that it runs to the plate. Cream cheese frosting brings tang and softness, but it is usually less firm than buttercream because cream cheese contains more water. Meringue-based frostings, like Swiss or Italian meringue buttercream, start with egg whites and sugar heated or whipped into a foam, then enriched with butter. They are smoother and less sugary on the tongue, but also more sensitive to temperature during mixing. If the butter goes in while the meringue is too warm, the frosting can slump. Too cold, and it may look curdled before it smooths out. Then there are fillings, which give the cake contrast. A fruit preserve adds brightness and a slight stickiness that soaks gently into the crumb. Lemon curd brings acid, egg yolks, and butter, making it glossy and soft. Pastry cream, thickened with starch and egg, can hold between layers if kept cool. Chocolate fillings can range from soft pudding-like creams to dense truffle-style layers. Even a thin band of raspberry jam between vanilla layers changes the whole slice by adding sharpness against sweetness. Once layers are stacked, cake becomes partly an engineering problem. Each layer may weigh 400 to 700 grams before frosting, and a finished celebration cake can weigh several kilograms. Soft fillings can squeeze outward if too much weight is placed on them. Warm frosting can let layers slide. Tall cakes often need chilling between steps so the fat can firm and hold everything steady. Very tall bakery cakes may even use dowels, which are small support rods pushed through the layers to keep the structure from leaning or sinking. So frosting and fillings are not decorations added at the end. They are part of the cake's final architecture, shaping texture, flavor, temperature, and stability all at once. And once those surrounding layers come into view, it becomes easier to see that cake is not one single thing at all, but a whole family of forms built on the same basic idea. That shared idea can take on very different textures, and those textures change the whole experience of cake. Two slices may look similar from across the table, both pale yellow, both frosted, both cut into neat triangles. But once a fork goes in, the differences become obvious. One cake may feel rich and close, breaking into soft, buttery crumbs. Another may spring back lightly when pressed. Another may seem almost airy enough to vanish. Those differences do not happen by accident. They come from formula and method, from how much fat is used, how much air is trapped, and what kind of structure is asked to hold the whole thing up. A butter cake is one of the clearest examples. This is the familiar birthday cake style many people know well. It usually relies on butter for richness and baking powder for lift. A typical butter cake might contain roughly equal weights of sugar and flour, with a large amount of butter and 2 to 4 eggs, for a pair of 8 or 9-inch layers. Because the fat coats the flour and limits gluten, the crumb stays tender. Because the butter is often creamed with sugar, the cake also begins with lots of tiny air pockets already built in. The result is a cake that feels soft, rich, and fairly fine-grained. When cool, it holds a clean slice. When brought to room temperature, it becomes more tender and aromatic because the butter softens. That is why a butter cake fresh from the refrigerator can seem firmer than the same cake an hour later on the counter. A sponge cake works differently. Instead of relying mainly on butter and chemical leaveners, sponge cakes depend heavily on eggs whipped full of air. In a classic Genoese, whole eggs and sugar may be beaten for 5 to 10 minutes until thick and ribbon-like. Then flour is folded in carefully so the foam is not lost. Some sponge cakes use little or no baking powder at all. Their lift comes mostly from trapped air and steam. That gives sponge cake a lighter, springier texture. If you press it gently, it may bounce back. Its crumb is often more open than a butter cake, with a slightly elastic feel. This is one reason sponge is often used for jelly rolls, layered European tortes, and cakes that will be soaked with syrup. It can absorb moisture without falling apart. Then there is chiffon cake, which sits somewhere between the two. Chiffon was popularized in the United States in the 20th century, and it combines two useful ideas: the moistness of oil and the lift of whipped egg whites. Oil stays liquid at room temperature, so chiffon cakes do not firm up the way butter cakes do when cool. At the same time, the whipped whites create a high, airy structure. The result is a cake that feels light, but not dry, delicate, but still moist. That balance is part of why chiffon often works well in tall tube pans. It rises dramatically, sometimes reaching 4 inches or more in height, yet stays soft for longer than many sponge cakes. Beyond those three, the category stretches even further. A pound cake is denser and more compact, built for richness rather than lift. A loaf cake, like banana bread or lemon loaf, often has a tighter crumb and a sturdier shape because it is baked in a deep rectangular pan. Flourless chocolate cake may use eggs, butter, chocolate, and sometimes ground nuts, producing a dense, almost truffle-like texture. Cheesecake stretches the idea of cake even more. Its body comes mainly from soft cheese, eggs, and sugar rather than flour. So its texture can feel creamy, smooth, and almost custard-like. So cake is not one texture, but many. Tender, springy, airy, dense, creamy, or close-grained. The methods may differ, the ingredients may shift, and the crumbs may feel completely unlike one another. Yet they all belong to the same broad family. And while texture explains a great deal about what the mouth feels, it does not fully explain why cake can seem so comforting. That part reaches a little deeper, into memory, expectation, and the way flavor is experienced in the mind as much as on the tongue. That deeper part begins with the body itself. Long before anyone learns what a birthday cake is, or what vanilla means, or what kind of frosting they like best, the human body already has a built-in response to sweetness. On the tongue are taste receptors that respond to sugar and other sweet compounds. When those receptors are activated, the brain reads it as a source of quick energy. From a biological point of view, that makes sense. Sugars are easy for the body to use. A sweet food is often a food that can provide fuel fast. That does not explain everything about cake, but it helps explain why sweetness feels inviting rather than neutral. A plain white cake may contain 30 grams or more of sugar per slice, depending on size and frosting. The tongue registers that sweetness almost immediately, often within a second or two of the first bite. The effect is simple and direct. Sweetness does not need much decoding. It arrives quickly, and for most people, it is read as pleasant. Fat deepens that feeling in a different way. Butter, cream, egg yolks, chocolate, and frosting all contain fats that change how flavor moves through the mouth. Many aroma compounds dissolve well in fat, which means fat can carry flavor and release it more slowly. That is part of why buttercream feels richer than plain sugar syrup, and why chocolate ganache seems fuller and longer lasting than a thin glaze. Fat also changes mouthfeel, which just means the physical sensation of food in the mouth. A low-fat sponge can feel light and dry. A butter cake at room temperature feels softer and smoother because the fat melts gradually as it warms on the tongue. Since body temperature is around 98.6 degrees Fahrenheit or 37 degrees Celsius, many cake fats begin softening or melting during the act of eating. That creates the creamy coating quality people often describe as indulgent or soothing. Then smell enters the picture, and smell is where memory becomes especially important. The part of the brain that processes smell is closely linked with areas involved in memory and emotion. That is one reason a familiar aroma can bring back a place or a moment so quickly. Vanilla is a good example. The main aroma compound in vanilla is vanillin, and even a very small amount can make a cake smell sweet and familiar before it is tasted. Cinnamon works similarly, but in a spicier direction. Chocolate brings roasted notes. Baked apple or banana adds fruit aromas shaped by heat and sugar. These are not just flavors. They are signals the brain has often met before. For many people, vanilla cake may be tied to school parties, grocery store sheet cakes, or family birthdays. Cinnamon may call up autumn baking, holiday desserts, or breakfast pastries. Chocolate cake may suggest celebration, reward, or comfort after a long day. The exact memory changes from person to person, but the pattern is common. Familiar smells do not arrive as empty data. They arrive carrying associations. Texture adds another quiet layer. Cake is usually soft. It yields easily to a fork and then to the mouth. It does not ask for much effort. Compare that with a hard cracker, a crusty loaf, or a chewy caramel. Those foods can be satisfying too, but they ask more from the jaw and the teeth. Cake often feels gentle because it is physically easy to eat. That softness matters more than it might seem. Babies, older adults, and people feeling tired or stressed often gravitate toward foods that are easy to chew and swallow. Softness can be read by the brain as manageable, safe, and low effort. A tender crumb, a smooth frosting, a soft fruit filling, all of that contributes to the sense that cake is not only sweet, but kind. So the comfort of cake does not come from one thing. It comes from sweetness signaling energy, fat carrying flavor and softness, aromas linking to memory, and texture making the whole experience feel easy and familiar. And once memory and comfort become part of the story, it becomes natural to look beyond a single kitchen and notice how many different places have created their own versions of cake. And the differences can be surprisingly large. In some places, cake rises tall in frosted layers and arrives at the table as the center of a celebration. In others, it is steamed instead of baked, wrapped instead of iced, cut into small squares for tea, or built from honey, nuts, rice flour, or fresh cheese, rather than the butter and vanilla formula many people first imagine. In Germany, for example, a famous celebration cake is Schwarzwälder Kirschtorte, known in English as Black Forest cake. It is made with chocolate sponge, whipped cream, cherries, and kirsch, a clear cherry spirit from the Black Forest region. The look is theatrical, dark crumbs around the outside, cream piled between layers, cherries on top. But it is also tied to a specific place and a local fruit tradition. In Eastern Europe and Russia, honey cakes became a different kind of classic. Medovik is built from thin layers flavored with honey, sometimes 8 or more layers, with cream between them. Honey matters here not only for sweetness, but for aroma and moisture. It gives the cake a deep golden flavor very different from plain white sugar. In Britain, fruitcake took another path. A traditional Christmas cake or wedding cake may be packed with raisins, currants, candied peel, and spices, then fed over time with small amounts of alcohol such as brandy. That aging can last for weeks. The result is dense, dark, and long-keeping, almost the opposite of a fresh sponge meant to be eaten the same day. Other regions lean toward lighter textures. In Japan, castella became popular after Portuguese traders introduced sponge-style cakes in the 16th century. Castella is usually made from flour, eggs, sugar, and syrup or honey, with no butter at all. Its crumb is fine, moist, and springy, and the cake is often baked in long rectangular molds and cut into neat blocks. It feels simple, but very deliberate. Steaming also changes what cake can be. In parts of China and Southeast Asia, steamed sponge cakes are common, where moist heat replaces the dry heat of an oven. That gives a softer, more humid texture and a very pale surface, since there is much less browning. Rice flour often appears in these traditions because rice grows well in warm, wet climates where wheat has not always been the main grain. That is one of the clearest patterns around the world. Local ingredients shape the cake. Where dairy farming was common, butter and cream became more central. Where sugarcane grew, sweet cakes expanded differently than in places where honey stayed important longer. In tropical climates, coconut milk, pandan, banana, cassava, or palm sugar often enter the picture. In colder regions, dried fruit, nuts, and preserved ingredients are more common because they store well through winter. Some cakes belong to ordinary days: a slice of plain loaf cake with tea, a small snack cake bought from a bakery on the way home, a simple yogurt cake made in one pan. Other cakes belong very tightly to the calendar. Birthday cakes, wedding cakes, Easter cakes, holiday fruit cakes, festival honey cakes. In many places, the cake is not just dessert, it marks the day itself. And these traditions have not stayed sealed off from one another. Global exchange has mixed them for centuries. Castella came to Japan through Portuguese contact. Layer cakes in many countries borrowed techniques from French and Central European pastry. In the United States, chiffon cake, created in the 20th century, blended modern oil-based softness with the lift of European-style foam cakes. Today, it is common to find cakes that mix matcha with French cream, mango with sponge layers, or tres leches with modern birthday cake decoration. So cake is not one object traveling unchanged across the world. It is a flexible idea, shaped again and again by grain, climate, trade, religion, celebration, and local taste. And from there, the story moves into a more modern setting, where cake becomes not only something made by hand for a special day, but also something produced at scale, boxed, transported, and made consistent enough to appear almost anywhere. And once cake enters the modern era, it begins to live in two very different worlds at the same time. In one world, it is still homemade and ceremonial, mixed in a bowl for a birthday or brought out after dinner. In the other, it becomes a product of factories, truck routes, freezer rooms, packaging lines, and supermarket shelves. A commercial cake has to do more than taste good for 10 minutes on a kitchen table. It may need to stay soft for days, survive shipping, keep its shape in plastic packaging, and look almost identical from one batch to the next. That changes the science. Consistency becomes just as important as flavor. Industrial baking is built around predictability. A factory cannot rely on a cake that rises beautifully one day and sinks the next. So manufacturers standardize almost everything: batter weight, pan size, oven time, mixing speed, cooling conditions, and ingredient behavior. A snack cake made on a large line may be portioned by weight, within a few grams, so every piece bakes evenly and fits the wrapper the same way. At that scale, cake is not only dessert, It is also process control. That is where ingredients like emulsifiers become especially useful. An emulsifier is a helper molecule that keeps water and fat from separating too easily. In cake manufacturing, that matters because batters have to stay smooth, aerate well, and bake into a fine, even crumb. Common examples include lecithin and mono and diglycerides. They help distribute fat evenly, improve volume, support a softer crumb, and make the batter easier to process on large equipment. In simple terms, they help cakes behave themselves. Shelf life becomes part of the design too. Cakes do not only go stale because they lose water. Part of stalling comes from starch retrogradation, which means the starch molecules slowly rearrange themselves after baking and make the crumb feel firmer. Commercial bakers work against that with formula design, emulsifiers, enzymes, packaging, and careful moisture control. The goal is not immortality. It is a cake that still feels soft and pleasant on day 3 or day 7, instead of becoming dry and disappointing. Packaging matters for the same reason. Plastic wrap, trays, seal film, and sometimes freezing all help protect texture during storage and transport. A frosted supermarket cake may spend time in a bakery department cooler, then in a display case, then in the back seat of a car, then on a kitchen counter before it is ever sliced. Its frosting has to hold shape. Its layers cannot slide. Its box must protect the edges from being crushed. The science of cake, at that point, includes cardboard strength and delivery timing right alongside flour and eggs. Box cake mixes bring part of that industrial logic into the home kitchen. In the United States, Betty Crocker was created in 1921, and by 1947, General Mills had released a ginger cake mix. Those mixes helped turn cake into something faster and more repeatable for home bakers. Instead of measuring flour, sugar, leavening, and flavorings from scratch, a person could open a box, add a few wet ingredients, and get a fairly reliable result. That reduced the number of variables the baker had to manage. And that reduction matters more than it first appears. Scratch baking asks the cook to measure accurately, choose the right flour, balance leavening, and mix well. A box mix has already handled much of that behind the scenes. The flour is chosen, the sugar is portioned, the leavening is balanced, and the dry ingredients are blended evenly. The home baker still matters, of course, but the margin for error gets smaller. In a quiet way, boxed mixes are one of the clearest examples of food science making a complex process feel ordinary. So store-bought cakes and mixes reveal another side of the story. Cake is not only chemistry in a bowl or warmth in a kitchen. It is also manufacturing, packaging, transportation, timing, and shelf life. And once cake enters everyday life that fully, it makes sense to pause and look at what it means for the body, as well as the senses. That body side is easiest to understand if we keep it simple and calm. Cake is usually what nutrition experts call energy dense, which just means it packs a lot of calories into a fairly small amount of food. That happens because cake often combines 3 concentrated ingredients at once: flour for starch, sugar for quick carbohydrates, and butter, oil, cream, or frosting for fat. Fat carries about 9 calories per gram, while carbohydrate carries about 4 calories per gram. So once sugar and fat appear together in the same slice, the total climbs fairly quickly. A plain unfrosted sponge cake can be relatively modest. a slice weighing around 50 to 60 grams might land somewhere near 150 to 200 calories, depending on the recipe. But a large slice of chocolate layer cake with frosting can easily reach 350 to 500 calories or more, especially if it includes buttercream, ganache, or extra filling. A bakery slice cut from a tall celebration cake may weigh well over 100 grams, which means it is not just bigger in appearance. It is a completely different nutritional experience. Sugar changes the experience in another way too. Because cake is sweet and soft, it is often easy to eat quickly. It does not require much chewing. It breaks apart easily, and frosting melts fast at room temperature or body temperature. That can make a slice disappear in a few minutes, especially in a social setting where people are talking, standing, or celebrating. A food that is soft, sweet, and already portioned onto a plate often goes down faster than something dense or savory. Celebrations make that even more likely. At a birthday party or wedding, people are not usually studying the crumb or measuring the frosting. They are singing, talking, taking pictures, or waiting for the candles. Cake in that setting acts less like fuel and more like a ritual object. A slice may be eaten after a full meal, simply because the moment calls for it. That does not make it strange. It just means cake belongs to a social pattern as much as a nutritional one. And not all cakes are built alike. A plain angel food cake is mostly egg whites, sugar, and flour, with no butter at all, so it is often lighter in both texture and calories than a frosted butter cake. Cheesecake is much denser because cream cheese, eggs, and sugar bring more fat and less air. Fruitcake is compact and rich, often full of dried fruit and nuts. A tres leches cake may be soaked with 3 kinds of milk, which changes both moisture and sugar content. So the word cake tells you surprisingly little on its own. The style matters, the frosting matters, the portion size matters. There is also the question of fullness or satiety, which just means how satisfied a food makes a person feel afterward. Cake can be filling in the short term because it is rich, but its high sugar content and soft texture can also make it less steady than a meal built around protein, fiber, and slower digesting foods. That is one reason cake tends to work best as a dessert, a treat, or a shared food, rather than the nutritional center of a day. And that may be the clearest way to think about it. Cake is usually not built to be a foundation food, the way beans, rice, eggs, vegetables, yogurt, or bread might be. It is built to be pleasurable, to be shared, to mark an occasion, to make a table feel a little more festive than it did an hour earlier. So looking at cake through the body does not take away its meaning. It just places it more accurately. It is an energy-rich, highly variable, socially powerful food, one that can be light or heavy, plain or extravagant, small or oversized, depending on how it is made and served. And with both the body and the social meaning now in view, the whole story is ready to come together. What comes together, in the end, is something much larger than dessert. Cake seems ordinary because it is so familiar. A round layer cake on a table, a loaf cake under a kitchen towel, a sheet cake in a grocery store box with a plastic lid. These are common sights, but familiarity can hide complexity. A cake looks simple only from a distance. Up close, it is chemistry. A shift of 20 grams of flour can make a batter stiffer. An extra egg yolk can deepen the color and soften the crumb. A few grams too much baking soda can leave a bitter taste and a darker surface. Butter at 70 degrees Fahrenheit creams differently from butter at 50 or 85. Sugar delays setting. Acid wakes up baking soda. Starch swells. Proteins firm. None of that is decoration. It is the reason the cake exists in the form it does. A soft yellow layer cake and a sunken, heavy one may begin with nearly the same ingredients, but the balance between those ingredients decides almost everything. It is physics too. Air bubbles expand when heated. Steam pushes upward as liquid water turns to vapor. Heat moves from the metal pan into the outer edge of the batter first, which is why the rim sets before the center. Gravity pulls on tall layers. Cooling changes structure because moisture keeps moving after the cake leaves the oven. Even a fork cutting through a slice is a small physics lesson in pressure, resistance, and crumb strength. Cake may feel gentle, but the forces shaping it are exact. And then there is history. The cake on a modern table carries pieces of many older worlds inside it. Honey cakes in the ancient Mediterranean. Sugar arriving through long trade routes. Refined flour from improved milling. Chemical leaveners developed in the 19th century, which made lighter cakes easier to bake at home without depending on yeast. Box mixes in the 20th century, which turned cake into a faster and more repeatable part of everyday life. Each step changed what cake could be, who could make it, and how often it appeared. Culture stays inside it too. A Black Forest cake, a Japanese castella, a Russian honey cake, a British fruit cake, a frosted supermarket birthday cake from North America. These are all cakes, but they do not mean exactly the same thing. They use different grains, different fats, different sweeteners, different traditions of serving and sharing. One cake may belong to Christmas, another to weddings, another to a quick afternoon snack with tea, another to a child blowing out candles while everyone counts together. And that is where cake becomes emotional as well as scientific. It often appears at moments of change. Birthdays mark another year. Wedding cakes mark a beginning. Holiday cakes return with the calendar and tell people the season has come around again. Even a simple homemade cake can mean that somebody had the time to measure flour, soften butter, preheat the oven, and make something meant to be shared. That may be why cake feels larger than its ingredients. It is not only flour, eggs, sugar, and fat. It is also waiting for the timer, smelling vanilla in the kitchen, watching frosting spread across cooled layers, hearing plates touch the table, seeing the first slice lifted out and noticing the crumbs left behind. The science explains how cake works, but the feeling of cake comes from where it appears in life. And that may be the quiet lesson hiding inside something so familiar. Even the foods people know best are full of hidden systems. Heat, moisture, air, starch, memory, trade, ritual, time. All of that can live inside one slice. So cake ends up being a gentle reminder that science is not only found in laboratories or textbooks. Very often, it is already sitting in ordinary places, quietly built into the things people love most. Good night.